Right?
Right.
Okay, great. So that looks like
It's like okay. So last week we did use substitution, indefinite integrals. Indefinite is when you don't have numbers in this spot, and then the plus c goes at the end. We have not done use substitution with definite integrals, and it's a little different. So this will be a good review of like use substitution in the first place. Plus, we'll get into what do you do with the numbers. So I might rewrite this first, like, and maybe you don't need to do this, but I think some people see it easier if you write it as like to the 1/2. I'm doing number 8. Are we good? Okay. So I got like a big guy, little guy situation. So this part, if I took the derivative of, I would need a chain rule. That means my u is in this somewhere, so that's my big guy, that's my little guy. So u is equal to t to the third plus 1. So then remember du, in this case it'd be du over dt, would be 3t squared. And so I'm going to show all the steps. I know some of you were starting to skip steps the more you got used to it, but it's been a few days, so I'll throw them all on there. So then I would multiply both sides by dt to get to there. And then if I want to solve for dt, which I do because I want to be able to plug it right there, dt would be du over 3t squared. We just started 6. So if I go to rewrite this integral, I'm not putting anything with the numbers yet, because that I have to show you. That's new. Don't just put it's not 0 and 2. But if I look at the inside, I will have this and then du over 3t squared. So that t squared is still there. That I put the u in place of, and then this is the dt that I solved for. Remember, we can tell we're on the right track if things cancel. That's good. Those cancel. So then I would probably just take a 1/3 out. But you got a 3 on the bottom, so it's really like a 1 over 3. So I'll pull it up. Now you got two choices. One, in my opinion, is far easier. Choice A, which I don't recommend, would be to leave this as a 0 and 2. This 0 and 2 has to do with t's. Well, if you leave this as 0 and 2, everything you plug in has to be t's. So you could put t to the third plus 1 back in this spot. Use a 0 and a 2 here and just go like normal. I wouldn't recommend that. What I would recommend is we need to convert these two numbers to the u version of those numbers. Because I want to be able to do the problem in u's. I want to get out of the t's, get everything into u's, don't even go back to t's, and just plug in and get my number. Well, I do that by looking at this. U is equal to 2 to the third, t to the third plus 1. So 2 becomes 2 to the third plus 1, which is 9. So I got to plug these two things into here so I know what they are in terms of u. Then if I plug 0 in here, that becomes 0 to the third plus 1, which is 1. And now it's just fun. I'll definitely do it because it's been a while since we've done it. I might not remember what normal means, but that's like the trick part I want to show you. So now I'm going to integrate. So I would say, I got a 1/2 out here. Add 1 to the power, makes it 3/2. Multiply by the reciprocal of power makes it 2/3. And I've got a 1 and a 9. So I got to plug in the top minus plug in the bottom. You guys see that? I've got to plug in the top minus plug in the bottom. To me, it's easier to pull that 2/3 out now than worrying about it being on the inside when I'm plugging in. So I'm going to cross out that 2/3 and 1/3 and write it as 1/9. Sorry, 2/9. And then I can finally plug in. No, because you multiply across the top and across the bottom. So now I'll have 2/9 times 9 to the 3 halves minus 1 to the 3 halves. So reviewing how to do those fractional powers, remember you take the root first, so the second root or square root of 9, which is 3, and then you raise that to the power on top. This would be 3 cubes. So that's 27, and then 1 to any power is 1. And you can leave it like that. You can't leave it here because you got the powers, but you could leave it like this. Or you could say 29, 2/9 times 26, or you could say 52/9. This one's risky. 2 times 26 is getting big time. I don't know if we can do that. I mean, I'm not saying that to be sarcastic. Like, I could screw that up. Not when I'm pretty confident, but I can still screw that up. So that's a perfectly valid answer, is what I'm getting. But the answer's not my main concern here. It's the process. Question's not what I was doing. The only new thing is plugging in those two numbers for you. But also, it's been like 4 days. I'm guessing you guys didn't use those two numbers. It's always minus. You always plug in the top number minus plug in the bottom. That's just like the rule. Yeah. So let's do a different one because you already know the answers to those. Let's do. I swear people have more trouble with this than calculus. Let's say 8 to the. I'm getting crazy. I'm making it negative also. So you look at the bottom part first, you take the root. So that means what number to the 3rd power gives me 8. That's 2. You take that to the power up top. So 2 squared. And then what are negative exponents do? Flip things over. So that would be 1/4. Is that right? So like just going back to that one, square root of 9 is 3. 3 cubed is 27. Other questions? Yeah. Yes. So back when I was writing this down a few minutes ago, Matthew, I wrote down this. The 2 has to become 2 to the 3rd plus 1 because that 2 is related to the t's. We're doing the problems in u's now. So we have to switch these numbers to the u versions. So I'm plugging into whatever I said u was going to equal to get the new number. Is that all? I'm sorry, I should have been smarter. Did you not understand it the first time, or did you not write it down? Okay, then I apologize. Then I apologize. I thought you didn't write it down. That's what I was doing. That understanding is a lot. Other questions? No. All right, let's try 9. Looks a little more intimidating because the trig, but it's not bad. I'm going to do it on a separate page. However, to the cos times root sine. Sine times root cos. Cos times root sine. So I would first write it as sine of x to the 1/2. So I think that's easier than roots, and that's easier to see the big guy, little guy. Is it x or t? It's x or something. Okay, so again, I got to integrate, and I can see, like, if I were going to take the derivative of this part, I would need chain rule. So my u has to come from that. So my u is going to be the sine of x. Most of you just started putting your heads down to work. You want a chance to try it before I do it? Yeah, that's fine. get to change the boundaries. The numbers. Right here.
How we write like the brackets once you integrate. Like if you just do it on the right side and do the line, or do you want it?
Those are all acceptable. Where'd you see the line? Because I haven't shown that. So I'm just curious.
The answer has a line too.
Oh, does it? So when you integrate, like, if you have, like, let's just make it simple, the integral of 2x, you could say that's x squared, and it's from like 1 to 3 or something like that. You could actually say x squared 1 to 3, or you can put like little things. There's kind of 3 ways to notate it. I choose that one because I've just historically students have done best with this, but you could really choose. Yeah, cheat sheet and seal it. Make sure you plug in to change the boundaries. When I say boundaries, I mean the zero boundaries. So here I'm saying what my u and du, dx, and all that stuff is, like we did last week. Here I'm saying these are x numbers, and I want them to be numbers with u's in them, in terms of u, so I'm plugging in my 2 boundaries to get my new boundaries. And then once I get to here, my cosines of x cancel, so I have the integral from 0 to 1, u to the 1/2 times du. So the integral of u to the 1/2 is 2/3 u to the 3/2. So you could just do that if you want. I like the whole thing, but personal preference. Then I plug in the top minus plug in the bottom. So if I plug in the top, I get 2/3. I plug in the bottom, I get 0. So it's just 2/3. Question on that one? How many got to 2/3? Anything else I can help with? Let's look at, there's a couple in the homework that I would like to point out. Carter, you're right. You got a question? I know, 14 or 15 I wanted. 14. Okay, so take a look at 14 with me, please. The first thing I would try, especially because we're in the u substitution section, Maybe I rewrite it and bring that up. And then I'm going to look at, like, can I do U substitution? So, like, think through the U substitution, though, with me. That'd be my U. So what's du? It'd be like 18t, right? So if we follow through that, let's say u equals 1 plus 9t squared. Du would equal 18t times dt. So dt is going to be du over 18t. That's the problem. Is there anything that's going to cancel with that? There's not. So it's not going to work. So u substitution in this case does not work because this has nothing to cancel. So at that point is when, hopefully, you start looking at, okay, that it could also be tan inverse, cosecant inverse, all those inverses. All of the inverses, if you notice, have something squared in them, right? It's like 1 over 1 plus x squared, or 1 over the square root of 1 minus x squared. They all have an x squared. So once I've established that u substitution is going to fail, that's my next thing, is can I look at writing this as something squared? And I think you would agree that I could write it like this. Isn't that the same thing? And then I can do the problem with u substitution, but the u just changed. So that first method didn't work. But now, if I make u equal to 3t, du will equal 3 times dt, which means du over 3 equals dt. Now I can rewrite, I'm not going to put the numbers because I didn't fix those yet, but it'd be 1 plus u squared times, and dt is du over 3. This is like, I would say, one of the more difficult ones, where the u substitution doesn't work, and then you have to like remember trig inverses and then try u substitution again. So I'm just going to pull that out. A lot easier for me in my head if the 1/3's out there than like chilling here. Then I also have to figure out these numbers. So u is going to equal 3 times 1/3 and 3 times negative 1/3. So I'm just plugging these in to u equals 3t. So I'll just get negative 1 to 1. Finally, I'm at the place where I can integrate. So what's the integral of 1 over 1 plus u squared? Tan inverse of u. One third on the outside, negative 1 to 1. And I'm not worried about the plug-in. I'm not even, I won't put that problem out here. But that is one that, like, if your goals are 4 or 5 that you beat us, like, you're going to want to be getting some of those questions right. Remember, you only need like 2/3 correct to get 5, but yeah.
We're just not worried about values of tan inverse at all. We just like stop at that point.
Oh no, I was just being lazy. So it'd be tan inverse of 1 minus tan inverse of negative 1. Did they give you like, you cannot, did they give you a domain? Okay. So tan inverse of 1 minus tan inverse of negative 1. So with the unit circle, when you are at like 45, aren't the sine and cosine the same value? They're both root 2 over 2. So right there, I know tan of 45 equals 1. And then down here, tan of, this would be negative pi over 4. Wait, yeah, negative pi over 4 is negative 1 because now the cosine is positive and the sine is negative. So you have like negative root 2 over 2 divided by positive root 2 over 2, which is negative 1. So then this becomes pi over 4. That becomes negative pi over 4, and that you could leave. Seems to be. Weren't we going through the one the other day that we did first and second? Was that you? Does that help, Eric? Is that what you're getting at? So, do the U substitution ones in your book. Don't worry about the test prep. So you were going up to 20. And we're basically done with the unit. Tomorrow I'll give you a review packet or list of topics, something to practice. Thursday I'll give you an actual practice gateway. Friday gateway. We play it Friday, Monday, Tuesday. Everything as far as like
that sheet, there's nothing extra that
I don't think this is what you're asking, but I'm just being careful to say. I mean, you should know how to do like cosine of 45. That's not how the shit. Like, okay. Well, some people will come back and be, you didn't tell me you had to know how to do addition. Like, well, that's screwed. Obviously. Anyway. Yes, you're going up to remember how long. Actually, no, because you just like, but.
yes. You said we didn't have to add or subtract. That's 2 and 1.
You don't have to. Yeah. What's that last?
But
there's no more like things about that.
So what I should be doing when I'm doing that is
Ones on that. That might make a like a Kahoot. Everybody's looking really. Yeah. What's your question? I lost it.
I can promise you I don't like
It's not. But I think if it happens,
I'll probably slide up to
this is a story.
I would honestly
I want to show you something I've kind of forgotten about, and it doesn't really affect the way you do any problems. But no one has asked this question yet. I'm kind of surprised. So maybe you figured it out. Maybe you don't care. I don't know. I'm going to show you anyways. The question is, why isn't there a plus C when we do definite integrals? Yeah, that's good. You're the only one. So like I've told you, when you integrate 2x, we're going to get x squared plus c. I don't know if it's x squared plus 2, x squared plus 100, x squared minus 30, whatever. So why did I not put a plus c in these? Well, what we would do next is plug in the top, minus, plug in the bottom. So what happens to those C's? They go away. So they are, like, if you want to think of them, they're always there. It's just an indefinite integral. They go away. And that's not going to change the way you do any problem. If that was like a disconnect for anybody, I wanted to show you. Does that help?
I thought it was just not there because